It's our pleasure to host this webinar for you. This is our 91st webinar in the series of technical webinars that we are conducting every month. As a practice, we are conducting one webinar every month. So please follow us on LinkedIn and YouTube to make sure that you are updated about our latest updates. Today, we have an experienced panel of speakers. I am with my colleague, Mr. 𝐊𝐞𝐲 𝐀𝐬𝐩𝐿, who is the Managing Director, Principal Integrity and Safety Consultant. Madam Mubina Khatoon, she is Director, Engineering Services at Velosi. And Mr. Tony Williams, who is General Manager, Global Sales. So, agenda, since this, it is a quite technical subject, we will touch only theoretical and practical aspects of dead legs integrity management system in accordance with API 570 and API 574 standards. In this limited 2 hours, we request you all to follow us and keep asking questions to help us make this session as engaging as possible. So first of all, we will go through safety moments before we begin. Although most of us are in the comfort zone of our homes, we should be aware of emergency exits. We should keep a safe distance and generally take care of ourselves and those who are around us. So let me begin with the Velosi introduction. I will just give a brief introduction of Velosi, what we do, and where we are based in. Velosi is a leading global consultancy firm that provides asset integrity management, HSE, engineering, environmental, and software solutions to the clients in oil and gas, energy, power, and petrochemical industries around the world. We have our in-house proprietary software, VAIL-Plant, as well, which is developed by us. It is an industry-leading SAP-certified complete asset integrity solution that is currently being used by oil and gas giants such as ADNOC, Dragon Oil, SunUp, and many more. Founded in 1982 in Malaysia, Velosi Group was acquired by Apple Spain in 2011. And with about 42 years of experience, we have expanded our footprints to more than 86 countries worldwide. So far, we have completed more than 1,200 projects with 400 different clients. And by combining global coverage and local knowledge with our wide range of services, Velosi creates tailored solutions to complex problems. Here is the map showing our worldwide existence. So we provide services in a broad range of industries, including but not limited to oil refineries, GOSPs, gas and NGL plants, fertilizer plants, structures, offshore platforms, wellheads, pipelines, and many more. Giving you a brief touch of our services, I will just cover the main topics that include asset integrity management services, under which we provide RBI, pipeline integrity management system, structure integrity management system, pressurized equipment management system, safety integrity level, condition assessment studies, asset life extension studies, corrosion management plan, DCVG, and CIP service. Then, under the umbrella of health, safety, and environmental services, we are covering HSEIA studies, process safety and risk studies, environmental studies, under which we are covering everything from environmental impact assessment to environmental management plans to environmental modeling and assessment. Then we have occupational health risk assessment, which is OHRA, under which we are covering emergency management and planning, qualitative OHRA, quantitative OHRA, workplace exposure monitoring, etc. Then we have the umbrella of engineering services, under which we provide conceptual design feeds, operating manuals and procedures, design verification and appraisals, FFS. And as discussed, we also provide software solutions. We have developed our in-house softwares, including VAIL-Plant, which is an asset integrity management system, VAIL-PHA, which is a process hazard analysis, then VAIL-PRA, which is petrol station risk assessment software, and then VAIL-MTS, which is material tracking system, VAIL-ERP, as the name suggests, enterprise resource planning, VAIL-CTR, VAIL-ORP, VAIL-Flow, and we are also working on many other softwares which are under development. Then we also provide audit and assessment services under the covering OHSAS safety audits, technical audits, environmental audits, structural audits, PSMs, electrical audits, flammable storage facility audits, etc. Velosi also provides ISO consultancy and training services to its clients, and we have so far covered ISO 9001 quality management system service, then ISO 14001 OHSAS 18001, which is occupational health and safety management system, and ISO 45001 occupational health and safety management system. Then we have also provided this ISO consultancy and training services in ISO 50001 and ISO 55001, which is asset management system. We also provide various trainings to our Velosi Training Institute LLC, established in Abu Dhabi, from certified technical programs to food safety training. Our training categories let you quickly select your chosen course and ensure you remain at the forefront of development throughout various industries. So far, we have provided the below mentioned trainings, which include certified technical training, exam preparatory training, HSE training, food safety, IOSH training, NIBOSH training, admin and business related trainings, etc. So as we have mentioned that we have our in-house developed software. So first of all, there is VAIL-Plant. We will like you to see the dashboard of the VAIL-Plant, which is covering CMMS, ISMS, APMS, EIRMS, PSPMS. So it shows that it is a single resource software solution that allows oil and gas operators to identify critical assets. So it is built on modular framework, and you can see multiple module windows in the main dashboard of VAIL-Plant. The VAIL ERP, which is Enterprise Resource Planning Software, it supports storage of assets data and associated management-related activities and documents in one central location. So under ERP, as the name suggests, Enterprise Resource Planning Software, there are multiple modules covering accounts, HRMS, payroll, CTR, which is cost, time, and resource management system. Then sales and purchase, CRM, which is customer relationship management, assets, material tracking system, project management, and others. Our third software is VAIL CMMS, which is computerized maintenance management system. It is a powerful tool that keeps track of information about an organization's maintenance operations, and it helps the management to make informed decisions by planning, scheduling, executing, and optimizing maintenance operations, resources, and materials. So this is the dashboard of VAIL CMMS, under which you can see there are work orders, notifications, maintenance plans, and there are multiple things that this software is capable of doing. VAIL PHA, process hazard analysis software, under which we have SIL and HAZOP. So during the engineering services, we use multiple inspection equipment. These are some of the equipment which we'll just quickly go through: magnetic flux leakage, coating thickness measurement, ultrasonic pulse velocity, then positive material identification, tank weld inspection, wireless dynamometer, tension load cells, ultraviolet imaging, current testing, resistance testing, holiday detectors, ultrasonic flaw detectors, PAUT, TOFT, advanced UTs, RJ protectors. These are the equipment which we use during our inspection in engineering services. So as I mentioned before that we have completed more than 1,200 projects in more than 400 clients worldwide so far. These are some of the clients we are proud of working with, like ADNOC, Dragon Oil, TANUP, BSR, BAPCO, Repsol, GRN, BMC, Madan, Lukoil, etc. So Velosi is certified for multiple certificates with ISO. So you can see that these certificates from ISO 9001, which is quality management, ISO 14001, environmental management, health and safety. We are also certified with SAP and Exida for integration of VAIL-Plant with SAP and third-party software.
So the subject is interesting, and it is very relevant to our day-to-day integrity issues, what we are facing or what we are used to face in the running plants. So if we see, is a technical webinar, technical knowledge. So it cannot be like so sweet like any movie or drama or any poetry or fiction. It is a science, and we have to go by the code of practice and how it goes. So what is dead leg? Basically, it should be called as piping dead leg. When we say piping dead leg, mean the area where there could be no flow, low flow, sometime also could be, basically should be no flow, and dead end of the piping systems. Like if you see this piping system here, there is a normal flow valve and there is a bypass. There will be a simple bypass and there will be bypass valve. So if one of the control valve is being used, other one is not being used, so there could be a no flow for a long period in this part. This part is called like dead leg. Similarly, there is a bridle across the vessels to measure the level, pressure, temperature, transmitters. So this area is generally no flow, is also called dead leg. Similarly, there are like this flange connection, small one, or there could be a small drain in the bottom. So the areas where generally there is a no flow are called piping dead legs. And this is the definition of API 574, or definition of API 570. Another example, like generally there are two pumps at the facilities A and B. One pump is generally working, another pump is on standby. So if operation, there is a sequence like one pump will be working 15 days, other pumps would be working 15 days. If the technical team or operation team forget to restart the other pump, but they keep running one pump, so that area around that pump will become the dead leg, right? So this is another area, one example of the dead leg. Similarly, there are PSVs upstream portion and downstream portion towards the flare. That is also a dead leg. Similarly, there are drains system. If you are not draining the fluid from the vessel or a pump or from equipment, then that segment of the piping system will never be used. So that is also called basically dead leg. So dead legs are there, and if there is no flow in these dead legs, there could be a stagnant fluid, there could be a dirt, and there could also be some accumulative material which could be more corrosive. And if the proper dead leg management program is not developed, so it may lead to a failure and leakage and rupture. There are incidents. So nowadays it is believed the main issues are coming from the dead leg portion than the normal plant. So what is the objective of the dead leg management system? As I explained, there are issues with the dead legs of the piping system in the process plant, where more aggressive corrosion taking place, and that is causing leakages and failures. To avoid that, so first of all, we need to identify all the dead leg in the plant. Take appropriate action required to maintain asset integrity and safety. Establish a risk-based process for managing internal corrosion of the piping dead legs based on the potential corrosion rate of unstable dead legs, the actual corrosion rate of the dead legs that are stable, the estimated severity of the consequence should a loss of containment occur, should be considered. Like if a dead leg fails, what will happen to the atmosphere, what will happen to the safety and health of the operators, or there could be a potential fire or explosion as a result of the failure of the dead leg. So why dead leg is a concern? See, if a dead leg will fail, it can cause leakage, rupture, and that leakage and rupture, if fluid is flammable, that flammable fluid find the ignition source. So in that scenario, there could be a fire or explosion. So we know that there are certain damage mechanisms which are more aggressive in a stagnant situation of any piping system. So we need to take care of that, and there are major integrity threats what we need to keep in mind. Here, this is like some addition we have done as compared to the previous case. In 2019, TPC Group Part Niches Operation Texas, piping dead leg rupture due to buildup of popcorn polymer, a reactive solid that accumulates in the high purity butadiene process. So approximately 6,000 gallons of butadiene were released, forming a vapor cloud that ignited, causing a massive explosion. There were two injuries, one security contractor also were basically affected, and this fire continued for about a month, and it affected the evacuation up to 4 miles, 4 means about 7 kilometers around the facility. You can see this photo, and we have taken this video from the web page, which is also referred here, keeping the respect of the copyright. So Identified causes were dead leg management failure. Second one, inadequate process hazard analysis, like they could not foresee it can go wrong. Then lack of emergency isolation valves were not there. Then poor internal policies to control popcorn polymer controls. Then what was the lesson learned? The regular identification and management of the dead legs in the high risk areas. Then timely implementation of the suggested safety actions from the hazard analysis, installation of emergency isolation valve to minimize the release duration, enhance internal policies for controlling hazard like popcorn polymers. So if we try to see this video, if we can work, let's see.
November 27th, 2019, the TPC Group chemical plant in Port
If
Neches,
you are
Texas.
able to hear this sound,
Release of highly
then
flammable
okay, this is the
butadiene
incident. What you
caused
can
a
see
series
there
of
is a
explosions that could be felt
video
up to 30
available
miles
on
away.
the YouTube
The blast
also, and we have
destroyed
taken
portions of the
this
TPC
video
facility,
from the
damaged nearby
YouTube
homes and
to
businesses,
show you
and prompted a
if
mandatory
we will
evacuation
not
of
be
residents
taking
living
care
within
of
4
the
miles of the plant.
dead
Several
leg
workers
at
and
our
members of the public
facility,
reported
we
injuries
may
and
have
fires
similar
burned at the
kind of
facility
fate.
for over a
Like
month.
we
At the time
learn
of the
more
incident,
if
the
we
company
see
produced
how that
butadiene
incident
at
may
its Port
happen.
Neches
So
plant.
that's why
Butadiene is
we
used as a
added
building
this
block in the
video
production of a
this
wide
part.
range of products, but it's most commonly used to produce synthetic rubber. It is a highly reactive chemical, which if not properly managed, can lead to serious hazards. On August 4th, 2019, a worker performed a routine operation in TPC's butadiene unit. As part of that operation, the worker shut down a primary pump that was part of the butadiene production process. When the worker tried to restart the pump, it would not operate. The primary pump was sent for repair and remained out of service from that date forward. A spare pump was used to continue operations. The inoperable pump created a significant dead leg, which is an area of piping that is open to the process but does not have any material flowing through it. The CSP determined that over the next 114 days, popcorn polymer began to form and accumulate within the dead leg. But the CSP could not find evidence that anyone at TPC recognized the hazard created by the dead leg. At 12:54 a.m. on November 27th, excessive popcorn polymer buildup caused the dead leg piping to suddenly rupture. Approximately 6,000 gallons of liquid, primarily composed of butadiene, emptied through the ruptured piping in less than a minute. The liquid vaporized upon release to the atmosphere, forming a flammable cloud. 3 nearby workers were startled by the rupture. They immediately recognized the danger and quickly departed as the vapor cloud grew. In just 2 minutes, the flammable vapor cloud found an ignition source and exploded. The resulting pressure wave destroyed parts of the facility and injured 2 TPC employees and a security contractor. The blast damaged nearby homes and buildings and was reportedly felt up to 30 miles away.
So this is one incident. There's also there's another incident which occurred in Oklahoma, natural gas pipeline explosion. It was January 30th this year. Location, rural Beaver Country, Oklahoma, near Texas border again. The failure in an 8-inch feeder pipe, dead leg, caused a fire and rupture in a main gas pipeline, resulted in a 5-foot long fireball, visible over 80 miles away. You can see the photo on the right. Then the pipeline involved was likely an unregulated gas gathering line with no enforced federal safety regulation of America. So the key takeaway is mandatory isolation of the dead leg pipes, enhanced crane monitoring, and regulation of the gas gathering lines. So with 2 incidents, we're trying to prove is like dead legs are important part of the facility and we need to pay special attention. And also in as per API 580, 581 and other statistical data of the reliability books, the failure rate of the small bores piping or the dead legs is highest. So to manage basically dead legs, we try to follow 4 steps. First of all, identification of the dead legs on the P&IDs, isometric drawings, and also making them known in accordance with the guideline of API 570 and 574. The second part, creating dead leg register. So as a hierarchy or a listing of all the dead legs, and the listing of all the dead legs is done by making parent-child relationship and the type of the dead legs, and also tagging and serials, and also its operating data, materials of construction data, corrosion and fluid data, and inspection records as well could be correlated with those dead legs as the inspection would be carried out. And once you have a dead leg register, then we can do risk ranking or criticality rating assessment by identifying probability of failure, consequence of failure. And then once risk is identified, then we can do the inspection planning also. Under probability of failure, we look at the applicable damage mechanisms and the growing rates, internal, external, both, and then see also taking care of the basically consequence of failure, like effects on the health, safety, or environment, and how much is the inventory and so on. Then once risk assessment is done, based on the risk assessment, we can also do like a mitigation program development or inspection program. Mitigation means if we can like do some kind of flushing or minimization or removal of the dead leg, more critical, or we have to develop inspection program, including visual inspections, UT inspections, or profile radiography or similar other advanced NDTs. So classification of dead legs, like if we go that like dead legs are like a permanent or a physical dead leg, one. Then operational dead leg, which could be like a standby pump. Permanent or physical dead legs are like, as we see the bypasses of the control valves, bridle of the vessels, then PSVs downstream and upstream portions, which are mostly no flow. And then second part is the operational dead leg, like a bypass of a control valve or a standby pumps. The two examples where operational dead leg comes. Then mothball dead legs are the dead legs where, like, if one portion of the plant is not being kept in operation due to any reason, and if a part of the plant is kept out of service for a certain period, months or year, then it may have high internal corrosion due to if it was not cleaned properly, not purged, and not mothballed. So that could also be, if when you put back in operation at that time, it can give some surprises. So mothballed dead legs are also required to be taken care properly. Then when we say permanent or physical dead legs, these permanent and physical dead legs are part of the basically piping isometric. If we see that sometimes there are extended pipe due to support reasons, or there could be a permanent, for example, vent or drain system which is installed at low point or high point, for the low point for the drain and high point for the vent, and that could also be becoming a permanent dead leg, and similarly other parts. So we have to identify which one is permanent and which one is like a physical dead leg, right? And how to take care of that. So the dead leg part, which are the main like worry for all operators, for example, bridle of a vessel or a column or a tank. Normally level gauges, level transmitters are installed, and there is also like a pressure transmitter, temperature transmitters, and in the piping system, we always see that there are drains at lower point and vents at high points, and then the bypass of a control valve, which normally only used when we take out the control valve for basically calibration or repair. And then other parts, as we said earlier, the PSVs, downstream and upstream portion, and if the pump is kept standby as the accident referred in the Texas case. So we need to identify which dead legs are permanent and which dead legs are like on the physical nature. Then operational dead leg, as example, give example earlier, the bypass of the control valves. Two control valves are there which should be alternatively used, or two pumps which should be alternatively used. So those are operational dead legs, piping system associated with those particular equipment. Mothball dead legs I explained earlier, like the portion of the facility which is basically put on hold for a certain period, months or year, due to non-operational reasons. If it is brought back to operation, then it has to be handled properly, and its condition should be assessed properly. Mothballing should be done with the due procedure, so as internal and external corrosions can be prevented during the mothballed duration of that particular portion of the piping system or the facility. The risk assessment or criticality ranking is like as per API 580, 581. The methodology for the risk and criticality ranking is same as we apply in any area PHA process, like what are the probability of the failure, mean what are the damage mechanisms, failure modes, internal, external, or escalation factors, absence of any corrosion inhibition or applicable flushing criteria and so on. So that will help us to calculate the probability of failure, and then consequence of failure as we estimate, like a production point of view, safety point of view, environmental point of view, health point of view. So all those aspects are calculated based on the volume and the nature of the fluid contained in that particular portion of the inventory group or isolatable section, and which is a part and parcel of the or associated part of the dead leg. And if the dead leg is rupturing or leaking, the whole fluid which will be coming out, that has to be considered and that has to be accounted for. So by the multiplication of the PUF and CF will give you the risk or the criticality, and that criticality rating can be used for the subsequent decision-making process. So as a normal risk matrix, there are 4 categories which are like a risk matrix or criticalities ranked high, medium, low, or negligible. So this scale, it varies from company to company, but in normal, like we can say if the fatality and the probability wise or severity or the probability wise factors are positioned in the risk matrix, that is high, then medium, low, and negligible, we can see in the next slide. And when we see the risk matrix, I will explain it further. If like we cannot reduce the high criticality or high risk of the of the dead leg, then we may have to think about redesign the plant, or like modify the plant so that dead leg could be removed. For example, like small bore connections, if we cannot like do any control on the effect of the corrosion, then better to remove and flush it off. Similarly, on the pumps like standby, we have to make sure the pumps are running, or we may have to make a plan or design aspect, like the pump both should be in operation somehow at some certain interval. So the redesign means if we cannot like remove that particular dead leg, so we should redesign the system if possible. Second one, like flushing is applicable on the bypasses of the basically like control valves, and flushing of the dead legs or the brittle of the vessels or the tanks, if we can do flushing, because there could be dirt accumulation. And similarly, upstream portion of the or downstream portion of the PSVs, which could be accumulating more low flow areas. The flushing is done with a flow rate 1.5 to 2.5 meters per second, so as the fluid inside or dead fluid or dirt could be removed from that part. So here, in general, class 1, 1/4 of the remaining life of 36 months, lesser of 1/4 of the remaining life or 36 months. Like whatever the remaining life is, 1/4 time should be used for flushing, or 36 months, whatever is greater, 3 years. So class 2 also 1/2 of the remaining life. Class 1, class 2, and class 3, class 4 are the API 570 classes. Because I'm not covering that part, so this class has to be referred from API 570. So then class 3 and class 4, basically 36 months is the interval for flushing. Then chemical treatment is we may have to inject like a biocide, so as bacterial growth could be flushed out, or there could be inhibitors. Inhibitors are either water soluble or the condensated oil soluble. So based on the nature of the fluid which is being contained inside the piping system, so we have to use suitably matching inhibitor, and that is the inhibition program is developed by each operating company, and they are using it. So then inhibitor through the drain valve, like there could also be you can use you can inject inhibitor from the drain valve if that portion is required to be treated based on the severity of that particular class. So here, while selecting inhibitor injection, so we have to determine the location of the drain valve, then serviceability of the drain valve, direction of the valve, then can fluid with inhibitor be injected into dead leg through this valve, and then we go for that particular injection process. Then assessment of the dead leg, This is like a condition assessment of the dead legs. For example, like if we can see externally, it would be maybe nicely painted, everything looks nice, but there could be high corrosion inside. So we have to check the internal condition of the dead leg as well by applying appropriate NDT technique. Simple one is if the big dia pipes are there, then we can do normal UT gauging or UT scanning. If it's a small bore where either we can use micro probe, if accurate micro probe is not available, then we may have to go for profile radiography, 3-inch and below or 2-inch and below, basically dead legs or small bore connections. So these two techniques are there. Then it could be also for the bigger dia, advanced NDT like a PAUT or TOFT can also be used if needed to the characterization of the metallography of that part. However, the more conventional techniques, visual followed by profile RT or UT gauging or UT scanning, which can give you a good idea about the health of the dead legs. And if it is insulated, then insulation removal or the thermography and those aspects. Thermography will not help in this particular case, but we have to remove some portion of the basically insulation, and then condition assessment of that piping system has to be done. Mitigation method, if you see here, like we have sketch like a flange spool, for example, low point drain. Then second one is level glass or level brittle on the vessel or a tank. Then differential pressure tape. So here the mitigation means like the first part, if replaced with alloy connection or blind flange with alloy slip blind, so it would be a less corrosion. So here they're saying if you have a small or flange spool low point drain, it should be high CRA material connection. Otherwise, carbon steel may have a more high problem for the corrosion. Similarly, it is instead of glass, the replace gauge glass for magnetic level indicator using corrosion resistant alloy material here. Now, under like a differential pressure kind of transmitter, here replace differential pressure piping with diaphragm sealed pressure transmitter so as the corrosion issues could be minimized. So these are some sort of redesign issues or mitigation issues which could be taken care at the new building stage of the facilities or new design stage of the facilities. Similarly, here, if we continue with the same mitigation, here the mitigation gas purge at the upstream of the PSV. So alloy PSV inlet piping and install like a metered gas purge to prevent corrosion and fouling at upstream of the PSVs, if it is possible. It could be downstream as well in the same way, so as or there is a proper slope in accordance with the 521 in the downstream portion of the basically the PSVs. Similarly, if there is a bypass of a heat exchanger, prefer not to have a bypass because this bypass is mostly forgotten and it has a potential of high corrosion in this portion. So removal of exchanger bypass, eliminating long dead leg example shown was over 4 meter long, this one. Now, condition monitoring locations, like where the we have to do more inspection. Right here, this is the bypass valve, which is more red. So this portion should be given more priority as compared to the flow. Yes, corrosion is everywhere applicable, depending upon the material of construction selection, applicable damage mechanism as a normal flow, and the dead leg. Dead leg will have a more potential for high corrosion. So there should be a more basically focus on that area. Then when we select basically the CML, TML points, like how many points it should be at that particular piping system. So we have to take care what is the corrosion class, what is the expectation of the corrosion type, general or localization, expected damage mechanisms, criticality ranking of the piping, and then whether there is a potential deposit of the corrosion like at the lower portion or upper portion of the piping system, if the pipe is insulated or not insulated. So keeping these all, keeping these all factors in consideration, we try to select the TML, CML locations in accordance with the guideline of 574. Inspection strategy. For example, like how a dead leg inspection strategy should be developed. like what we are used to do, for example, if there are small bore connections like vents or drains on the piping systems, so we can call profile radiography in one go, and we can do condition assessment of those piping systems like as a one campaign. Similarly, because the mostly piping inspection can be inspected externally if it is not insulated. If it is insulated, then the removal of insulated installation possibility depends upon the operating temperature of that particular segment. If we cannot like touch the pipe because it's too hot, then we have to inspect during the shutdown, or we can inspect the piping system during the normal operation as a online OSI program, like on-stream inspection program. So we have to keep in mind, like, for example, if here, if I go through my presentation points, assign CML to dead leg depending upon the potential and extent of the dead leg corrosion anticipated or previously experienced. Inspect dead legs as per interval prescribed by corrosion and operation engineers. For highly corrosive and toxic fluid circuit, monitor all the piping dead legs in a circuit where experience has shown that corrosive fluid, sediments, salts, and contaminated water collect in the dead leg. Then inspect particularly at locations where water and deposit can collect, allowing corrosion and microbiological activities or corrosion, like a biological corrosion or SRB's corrosion can be the more fast damage mechanism to act. Then bottom third of any horizontal piping, then branch connections originating from the lower half of the horizontal of the vessel. Then, like, inspect particularly at locations where water and deposit can collect, allowing corrosion and microbiological activity to develop, such as, for example, bottom third of any horizontal piping, branch connections originating from the lower half of the horizontal lines, low spots, bottom of vertical sections, above closed valves, sections of branch connections close to the main line, lowest parts of the vessel bridle work, together with any associated and level gauges. Upstream of concentric reducers, location where previous corrosion or erosion has reduced the wall thickness. In hot piping system, the high point area may corrode due to convective current setup in the dead leg. Then, like, what techniques? Like a simple one is the UT gauging or UT scanning. It can be applied in any, like a bigger pipe dias wherever access is possible. Then we can also use profile radiography for the small bore connection up to 3 inch is more effective. Then if accessible small bore piping, for example, 1 to 6 inch, class 0 and class 1 dead legs shall be RT. Like here where RT is being preferred and somewhere UT is being preferred, but up to small bore, RT, profile RT is more useful in my experience. Where radiation sensitive electronic devices would be affected, or for the sizes above 6 inch, UT scanning is in the lieu of the RT acceptable. Inspection of the horizontal dead leg that may not be liquid full should have examination point in all 4 like quadrants of any CML. Infrared thermography may be useful for locating liquid interfaces in the dead leg. Inspection should include profile radiography on small diameter dead legs such as vent and drains, and scanning UT or RT on longer diameter dead legs. Other examination techniques for dead legs include EMAT and PC as well. All inspection findings shall be evaluated as appropriate, with defect notification issued as necessary to document the deficiencies resulting from dead leg inspections. For inspection findings in which corrosion is suspected, consultation with the corrosion, metallurgical engineering, and operating team should also be done so as this threat could be minimized. Then frequency of the inspection, this is I think repetition what I discussed earlier also, but like for class 1, the inspection interval normally is same like flushing, and this also for the normal inspection. A lesser of 1/4 of the remaining life, or 36 inch, whatever is the lesser. Then for class 2 dead legs or piping system, lesser of 1/2 of the remaining life, or 36 months. Class 3 and 4, 36 months interval. Flushing guideline, like here, piping service class 1, piping service class 2, piping service class 3, piping service class 4. The corrosion type, general or localized, general or localized, general or localized. Then here, fluid corrosivity, high, medium, low. Then flushing frequency, monthly, quarterly, 6 monthly. What is the flushing velocity? It is a 1.5 to 2.5 meter per second. So these flushing guidelines are available, and these flushing guidelines can be used for flushing the dead legs where the dead legs were avoiding of dead legs were not possible. So now we went through like a general dead legs, what are the dead legs, how the dead leg can be managed, how the criticality could be done. So now whatever we are telling, that is based on the standards and best practices. The main standard and practices what we are used to follow, the main standard for the piping dead legs is API 570. API 570 got at least 6 parts and then appendices. First part, introduction. Second part is inspection, examination, and pressure testing practices, interval, frequency, and extent of inspection, inspection data evaluation, then analysis and recording, repair, alteration, and repairing of the piping system. Section 6 is inspection of buried piping. Then, like in the Annex A, inspector certification, request for interpretations. Then Annex C is example of repair. Then Annex D is 2 examples of the calculation of MAWP of the piping systems. So this is the index of API 570. If you wish to see more details, it is there like the same way it is starting from the chapter 4 owner user inspection organization, then inspection, examination, and pressure testing practices. Under that, RBI is also part of this case. Preparation for inspection is there. And item 6.6 is the extent of inspection on small bore piping, dead leg, auxiliary piping, and threaded connection, page 50. So certain guidelines are given here. This, the second standard, which is goes hands in hand, API 570, that's a 571, which is a damage mechanism affecting fixed equipment in refining industry. So damage mechanism and process unit process flow diagram, there are 2 parts. So here is the index of this particular basically, so I cannot enlarge it. So gentlemen, if you are ladies, if you want to ask any question, please ask in the question answer window, and we will be taking break in between, and we will be answering these questions, right? So next standard is API 574, right? And API 574 it's got about 10 parts. First one, introduction. Second part, piping component. Then piping pipe joining methods. Reason for inspection. Inspection plans. Frequency and extent of inspection. Safety precautions and preparatory work. Then inspection procedure and practices. Pressure test. Determination of the basically minimum required thickness is also part of the standard and their appendices as well. And here, if we try to see basically the component which are coming from API 574, like here, if I want to make bigger portion, piping components, then piping joining methods, then inspection plan, 7 section, frequency and extent of inspection, and similarly, there are other sections like a pressure test, then 12 determination of the minimum required thickness for the various conditions. Then API 580 is the RBI standard basically. And this standard got almost 12 sections. The low system resource may topic. There's a message coming on the screen. I hope you are not seeing that. So this standard got 12 parts. Basic risk assessment concept. I know the people who know RBI 580 certified, they would be knowing about it. But in this webinar, all level of people are attending. So sometime I have to touch base the basics. So API 580 is a basic risk assessment concept, introduction to the risk-based inspection, planning the RBI assessment, data and information collection for RBI assessment, damage mechanism and failure modes, assessing probability of failure, because the criticality assessment or risk ranking of the dead leg is a part of this scope of discussion. That's why I'm touching API 580 also as a part of this webinar. So assessing consequence of failure, risk determination, assessment, and management, risk management with inspection activities, other risk mitigation activities, reassessment and updating of RBI assessment, role responsibilities, training and qualifications, then RBI documentation and record keeping. So this is the basically the index of the API 580. We try to see as a part of this, like just have a little introduction. The basic risk assessment concept, then introduction to the risk-based inspection, then planning the RBI assessment, then data and information collected for RBI assessment. 8 is damage mechanism and failure modes, which takes to the 571. Then 9 number is assessing probability of failure. 10 is assessing consequence of failure. 11 risk determination, assessment and management. Then 12 is risk management, and 13 is other risk mitigation activities, and 14 is reassessment and updating of RBI assessment and so on. So then, like it is also having like RBI documentation and recording. 16, not 12. There's basically 17 sections are there in this standard. The next, like last standard in the row, is API 581, which is like a risk-based inspection methodology or guideline. Is a more detailed document. So here the part 1 is introduction, part 2 is probability of failure methodology in detail, part 3 is consequence of failure methodology in detail, part 4 is inspection planning and methodology in detail, then special equipment are also covered under part 5. So index wise, this got a very big index, so I will not go through each section. So it is same but more details, and like number of pages wise also it's a big standard. If you see here, like up to 126 pages are coming this, right? So this is a big standard, API 581. So if you wish to go through, you can go through, but I'm not covering that part as a part of RBI here. Then other companies like Shell and Saudi Aramco, they've also made their own like SOPs for the management of dead legs. So I'm showing you MEC management of dead legs. There is a Shell SOP, and there is also Saudi Aramco SOP. So these SOPs are also compatible with API 580, 581, and 571, 570, and 574 standards. They are basically these references are also given in these standards. So I'm just sharing with you, like whatever we are trying to do, it is also being adopted or being managed by the operating companies, and we are just assisting them to enhance this further. So now, before I go to the case study, we'll take questions at this stage, and the participants who are available, and they can ask questions by themselves by telling their name, their organization, and location from where they are speaking. So it will also, like other people would also be able to hear, and we can make this session a little bit more interactive. So my colleague, Mr. Ali Ahmed, will be assisting me in answering these questions. So Ali, over to you.
Sir, there is a question from Mr. 𝐊𝐞𝐲 We have allowed you to speak. Could you please ask your question, Mr. 𝐊𝐞𝐲? Sir, question is on your screen.
Okay, I can read the question. The asset integrity management software is for rotary or static asset or both of them, and what are the software capabilities like asset performance management etc. Here what we are covering is dead leg management system, right? And dead leg management system is part of the static equipment, and so asset integrity covers both, and there are various modules in our software which covers like a rotary site, static equipment, pipelines, structures, civil lifting equipment, rotary electrical instrumentation equipment, and it also covers like the health monitoring results as well as the performance management results.
The next question is from Mr. Troy. We have allowed you to speak. Could you please ask your question, Mr. Troy? Rafael Bio.
Troy Rafael Tubo or Tobo. Tobio.
Okay, sir. Question is on your screen.
Okay, can we put or install drain pipe in the dead leg to avoid rusting or corrosion in the system? is all the drain pipe, small bore connections, whether vent or drain, they are by definition are dead legs, and they should be kept as a part of dead leg register. It's a API 570, 574 criteria.
Okay, sir. Next question is from Mr. Vakar Ali. Mr. Vakar, we have allowed you to speak.
Whether the message is being heard by them.
Yes, this is Mr. Vakar Ali.
Nobody speaking today. Mute किया आपने? क्या mute तो करें? Mute है वो तो. They are mute. I can see that Mr. Bakar is mute.
Yeah, sir, we have allowed them.
No. If no one is able to speak, it means something wrong with the system.
The question is on your screen.
Okay.
We'll try.
Now you see that. Like Vakal is asking what sign or the system might indicate that a dead leg is present in a system, right? Basically, dead leg is by configuration or by geometry. We know that like if a bypass of a, like there's a handles are there, like there's a hand attendees, you can ask the person who is raising the hand whether he's able to speak, like Mr.
Okay, sir, Mr. Malik Mubin Mubarak Ali. We have allowed you to speak. Could you please ask a question? Malik Mubin Mubarak.
He's not hearing the question. Is it? Can you write in the window if you are able to hear us? And you're able to, are you willing to speak?
Mr. Muhammad Shafauz Qasim. We have allowed you to speak. Mr. Akib Iqbal. And then
You can try from your
Shubham. Mr. Shubham.
You can try your best. Looks like we are unable to hear them.
Mr. Hassan Mukhtar.
Go to the question, right? It looks like something with our system wrong. We are unable to hear them. Okay.
Hi,
Next
sir.
question.
I am Hassan Mukhtar.
Yes, Mr. Hassan Mukhtar.
Yes, sir. Yes, sir.
Please ask.
Sir,
Point is question.
sir, can we say API 570 provide the code for the pipeline and 574 provide the techniques which will use for NDT purpose in pipeline 574? Can we say?
No.
Sir,
See, API 570 and 574 both are complementing each other. So both are for the piping systems. For pipeline are covered under ASME 31.4, 31.8, and they are supplemented by up to a certain extent ASME 31.8S or API 1160, right? And then on the subcomponents we can use API 570 and 574. So in general, 570, 574 both are related to piping system, not for pipeline in particular. Okay, sir.
Okay. Thank you so much, sir.
Mr. Sabit Ali.
Mr. Sabat Ali, you have raised your hand and we have allowed you to speak. Could you please ask your question if you are available? Mr. Sabit Ali.
Can you hear me, sir?
Yes.
Sir, I have a question that the storage tanks that are closed from a significant period and that are not used from years, those are counted as dead legs or not?
See, if you remember, I made the point there are three types of dead legs. One is permanent one, other one is operational one, and third one is mothballed one, right? And if some equipment or part of the plant is not kept under normal operation for a certain period, let's say month, 6 months, 1 year, so those has to be managed like basically mothballed part of the facility. And there is a specific procedure which should be followed to manage the mothballed part of the facility equipment, including piping system. Okay, sir. If a tank itself, for example, or pressure vessel itself, you know that there's a fluid is there, it is being filled and emptied, and whether a floating roof is there or not there. So, but if the filling and emptying operation taking place, so bottom of the tank is taken care as a like a dead leg part because it is stagnant fluid, dirt, and there's a corrosion both from the bottom side, soil side, as well as from the process side. So we need to take care of those damage mechanisms and including biocide treatment if needed, drainage on the timely manner, there's a water accumulation. The removal of the water also is taken off from the drop of the water from the tank. So that is the mechanism which is managed in accordance with the API 653 guidelines. Okay, sir.
Thank you, sir. Thank you, sir.
Okay, so
You
sir,
can also tell like whoever is asking the question, their location and the organization from where they are working, so as other people will also be able to understand from where you are speaking. Next question.
the next question is from Mr. 𝐊𝐞𝐲 𝐀𝐬𝐩𝐞𝐬. Mr. 𝐊𝐿𝐲, we have allowed you to speak. Could you please ask your question, Mr. 𝐊𝐿𝐲?
Assalamu alaikum.
Walaikum salam.
Am I visible? So,
Yes,
am I
we can
audible?
hear you. Yes.
So my question was that if a pipe is like half filled during the operations, will the half portion, like the empty portion, will be considered as a dead end or not?
No.
Like normally
The-
it is like fully like उसमें कोई quantity उसकी empty नहीं होती कोई भी part की, लेकिन अगर वो half filled है तो उसका half portion जो empty है वो dead end consider होगा या नहीं?
See, dead leg definition is areas where there's a no flow. In the dead leg, if the half filled, it means there's a low velocity or the low flow situation. So low flow and dead leg are two different scenarios, right? Like in a heat exchanger, if the velocity of the fluid is lesser than, let's say, 3 feet per second, then there are chances of the fouling. And similarly, if in a piping system, if the turbulent level of flow is not, the velocity is on the streamline flow or laminar flow, then there could be another area, side of the effect. But dead leg definition wise or the dead leg management system does not cover that aspect of the plant operation. Thank you. Next question, please.
The next question is from Mr. 𝐊𝐞𝐲 𝐀𝐬𝐩𝐿. We have allowed you to speak. Could you please ask your question, Mr. 𝐊𝐿𝐲 𝐀𝐬𝐩𝐿? Sir, question is on your screen.
Is there a particular period was mentioned to call the pipeline was a dead leg? See, we didn't say pipeline is a dead leg. A pipeline could be a mouthwalled if a certain period of time pipeline is not kept under operation.
Velosi की लगा है, senior cast.
Yes, please. Okay. So that particular portion like has to be dealt as a mouthwalled portion, but pipeline as a whole is not called as a dead leg by definition. So there was one question whether we are presenting any case study. So case study is coming up and we will be presenting it, right? With this case study, at the end of the case study, there will be another like a last portion of the question answer. Please keep writing your questions, and if you are willing to speak, we'll also give you the floor and we will ask these questions again, right? So meanwhile, our technical team will look into the, like our system is working effectively. Slowly we start the presentation again and the question answer would be at the last again. So now I will be presenting a case study like dead legs and small bore piping integrity management program for a LNG complex. We completed this job almost, I can say, more than 12 years ago. So, and this same presentation available also on our YouTube, previous webinar done by my colleague. So it is a repetition, but this time we will be taking question answer in a live. Previously, we used to reply only through the chat window. So this would be a difference. And so if presentation is like of a different person, so otherwise our most of the material is same. If you wish to refer back our existing YouTube video, you can go back and look at that also. So here the objective of the project, which was assigned to us by the company, I'm not telling them the company because I did not take the permission to disclose their name. So to develop risk-based management program for dead legs and small bore piping systems and nipples, establish optimum inspection requirements of the dead legs and in-service existing small bore piping and nipples less than 2-inch NPS diameter with existing train 1 facilities. The scope of work will require the main steps below: marking of the dead leg on the basically PNIDs and isometric drawings, then performance of the risk-based assessment by using the company risk metrics, then develop inspection plans, WSM written scheme of examination, and specify applicable inspection techniques and the coverage and frequency in accordance with the applicable damage mechanism and risk category. Deliverables, high-level dead leg and small bore piping integrity management strategy document. Then this document was covering the inspection strategy, inspection techniques, inspection intervals, and extent of inspection of dead legs and small bore piping. The methodology for driving the inspection interval for dead legs and all small bore piping works. Assessment of CUI for the insulated dead legs and small bore pipe work. Dead legs and small bore piping anomaly management. Corrosion rate of dead legs and small bore piping nipples. The remaining life for dead legs and small bore piping nipples. The evaluation of dead legs and small bore piping nipples from the integrity point of view. Then define non-standard, not compliance with the PMC connections, if any, and recommend repair methodology for each one. Detailed inspection program for dead legs and small bore piping and nipples, degradation mechanisms, methods, and intervals. These were the basically were deliverables as per the agreement. Here, approach-wise, project kickoff meeting, then site data collection, preliminary reviews and site interviews, review of the PNIDs and arithmetic drawing, marking of PNIDs with dead leg and small bore connection, and preparation of master register, identification and verification of corrosion loops database, then perform RBI assessment, develop detailed inspection plan, WSC based on risk assessment, then preparation of detailed report. Methodology is the same, like collection and review of the engineering data, tagging and marking of small bore piping and nipples on PNIDs and arithmetic drawings, preparation of detailed dead leg, small bore piping and nipple master register, inspection history review, then identification of potential damage mechanisms, preparation of corrosion loops and circuits, LNG complex RBI assessment for the piping like dead legs and small bore connections. So people who are raising hands, I would advise to write question in the Q&A like a window, and we will be answering your questions at the end of this presentation before we go bye-bye. So Velosi RBI assessment of dead legs and small bore piping nipples, preparation of inspection guidelines, preparation of inspection sketches for main piping systems, dead legs and small bore piping and nipples. Then marking of PIR, NDT technique on isometric drawings, conclusions and recommendations. Here, like what data collection, what we have done, for example, here, like PNIDs, then PFDs, isometric drawings, then piping material specification, piping line list, inspection history piping, vibration survey results, and RBI assessment results also taken. Then PRBI risk matrix was also taken. Tagging and marking of the dead legs, like from and to, there's a piping system going on if you see that. Then there could be a one DLC1, DLC2, DLIC3, DLIC4. There could be 4 dead legs and their ID number is there. So tagging of dead leg is carried out on the basis of type of the dead leg and to and from the piping system. Small bore piping and nipples are further subdivided into SBP and nipple dead leg, for example, DL1C, DLBB, DLLNC, DRN, etc. There is a nomenclature which will tell you what kind of dead leg is this. I will explain further. The numbering of dead leg start from point of origin toward the end point of the main line for each type of small bore piping. For example, DLC1, DLC, like if the similar type of dead leg is there, a different type, then it will be covering the type of that dead leg also. Then common dead legs include bypass lines, drain lines, instrument connections, PSVs, inlet, outlet, headers, then dead end lines, vent lines, etc. Here, numbering, how we try to number dead legs, if those were previously not there, 24, 10, WGD, L 4102001 is area code, plant code, fluid service, then line number and DL serial tag number with the type of that particular dead leg. So area code, plant code, DL, service code, line serial number, sequential number of dead leg in the respective line. So these are like abbreviations or type of dead leg what we identified. For example, DLBB is a blanked branches, DLBL bleeders, DLBYP bypass line. Then there is a DLCP corrosion probe. Then there is a DLCVBP state control valve bypass piping. Then there is a drain, DRN drain. Then there is a DLERL cooler exchanger recirculation line. So similar way, we identified all the dead leg types, and then there is a serial number against each kind of dead leg. So the last one is sample point, DLSP, spare pump piping, DLSPP, then DLSC, like a sample connection, right? There's a sample point. Then spare filter piping, DLSFP. So each company can develop their own, but these abbreviations were developed by Velosi for this particular client. Once we have the type of the dead leg, then we mark those dead legs on the P&ID like DLRVI, DLIC, DL, LWNBB, and DL, DR, and drain. So whatever abbreviation we specified earlier, those are marked by identifying on each dead leg. This is the bypass of a control valve. Here, so say, like one time we mark on the basically P&ID. P&ID is a non-directional drawing. It does not have a length or scale or position. Then same dead leg is marked on the isometry, where we can see that this is a drain on particular piping system, DLDRN drain. So similarly, P&ID marking is a full P&ID marking. The first one done on the sample basis. Now it's a full, like here you can see all type of dead legs which are marked on various section of the pipeline. P&ID. You wish to see that, like this is the drainage system. This is a PSV's upstream downstream portion. Here small drains are there. So all type of dead legs, you can see there are many dead legs which are coming, whether they are the instrumentation small connections, vent point, drain point, or bypasses. So these are many where due attention has to be given. So similarly, detailed marking on actual isometry, you can see that this portion is shown as a basically drain isometric, and this is a dead leg. So what I know that a big number of people attending this webinar. So like what we are showing, this is how the work is done. So we cannot like make you master, but if you try to apply the similar approach, it will certainly help. Then preparation of dead leg and nipple master register, and under that register we try to serial number first unit wise, and then engineering data, operating data, inspection and failure history, RBI data, then inspection planning or RBI assessment results. So this is our software what we use VAIL-Plant, and here you can see the dead leg portions. There only engineering data is there, which is the material of construction, the service, operating conditions, the plant hierarchy, parent-child relationship also you can see here. Engineering data is like more detailed, if you can see. Now, if we try to see the asset register, so here the dead leg master register, serial number, plant tag number, installation date, equipment type, throw-in loop number, P&ID number, dead leg yes, no, and at the end child tag, which is the basically the dead leg. This is dead leg basically register coming here. Then from to and this area. Like how we reach to this, it is linked with the parent site. This is a parent tag with the one pipeline, which is having so many dead legs. If you can see that, 1, 2, 3, 4, one pipeline. And if the line number is changing, then it will have some certain changes in the list also. Then counting summary, for example, like how many dead legs we identified altogether. This is a result. For example, if you see that blanked branches in unit 121, 181, unit number 22, 141, unit number 24, 161, unit 25, 135, altogether 618. Here, total types of dead legs are 3,149. You can imagine that if there are so many dead legs and if they would not be inspected properly, these could be a weak leak for the plant and may have a surprise anytime in the form of the leakage. And this facility is now currently operating more than 50 years age. It means as a passage of age, dead leg would be more problematic. And there are failure occurring also. That's why this study was done at that time. So here, so now more detailed like dead leg summary, like a unit wise 120, 121, 123, 125, so on. So each unit and total 4828 other area of the, that was a one area, other area, 4,828 dead legs, which are identified in the PNIDs, which are identified on the isometric, the registry is made, and the inspection plan is also made. Then sample screenshot for dead leg piping master register, again same like more details like a company, train, plant number, equipment tag number, equipment type, component tag type, component type, and then dead leg yes, no, position from, to, and reflections. So here development of Corrosion loop, like we prepare the Corrosion loop for the same piping system, the dead legs are also coming. So here we try to identify all the damage mechanisms in accordance with APA 571. Like these are the damage mechanisms which are applicable which portion of the facility. Like a normal RBI process, we try to identify the applicable damage mechanisms. This is a case study, as actual example I'm sharing with you by eliminating the name. Here, then the damage mechanism which were already identified by the LNG complex, then additional what we identified, then final applicable damage mechanism on that particular unit of T11. Similarly, T12. This is summary only, and each area damage mechanisms are different, and it goes by Corrosion loop by Corrosion loop. So no inspection history record was available at that time, so we have done inspection later on. Here, risk is calculated probability of failure and consequence of failure in accordance with APA 581. According to APA 581 Part 2, Section 4, Table 4.1, generic failure frequency value as a function of hole size, like for the small bore, it is higher. This shows that the generic failure frequency GFF is higher for pipe 1, and hence the increase the PF value by 1 for nipple and dead leg. One stage. Here, how we do dead leg RBI, small bore connection, nipple dead leg. Then risk ranking for the small bore, like remains same as piping, it is a small bore piping. CF remains same as piping, whereas nipple dead leg, here risk ranking criteria of PF increased by one level as compared to piping. CF remains the same as of piping. Overall PF and CF and risk ranking is done. Now, the risk PF and CF and this risk matrix which is used. Under probability, we have considered fluid content, operating conditions, material of construction, installation status, damage mechanism, inspection, failure, and replacement history. And this is basically condition of POF, mean 1 to 5 scale, and 1 mean the failure rate is 1 out of 20 years, and 5 mean failure could occur between 0 to half year. Identify consequence of failure, inside fluid, safety, environmental effect, business and capital effect, all are considered. And on the COF side, classification on the negligible, low, medium, high, and extreme. Safety mean no injury to multiple fatalities, and capital loss goes from 0.1 million to 25 million, greater than 25 million. So this is also the actual risk matrix, which is of the operating company at that time. So this is basically the Velosi risk matrix what we used, which it looks like. So here we have done RBI assessment by assigning POF, COF for each equipment based on the inspection effectiveness. This is an older screen. Now our new RBI program is more updated and more visible. So here the applicable damage mechanism, as we can calculate the effect of the damage mechanism and their corrosion rates. Then this is the basically distribution of the equipment as per the risk matrix. If you can see here, like 58, 36, 19, 59, 597, the overall distribution of the equipment. Here, high risk equipment is identified as 107. Here, the color wise, you can also see high, medium, low. Like this color, red, then maroon, then blue, yellow, and green. So high 107, medium high 95, medium 6 to 9, low 89, 1. This for unit number 11, 12, and 13. This is unit 11 alone, the same distribution. Like high 45, medium high 07, medium 114, low 35, total 201. The 12 unit number unit, this is a distribution. There are items in the high risk. You can see that means the probability is failure is coming from 0.5 to 4 years, and consequence is coming on the extreme side, the 43 unit. And their failure rate 4 to 10, the effect could be the very high on the consequence side, 19 tax. This is unit number 13 result. So here is the summary of the philosophy of risk assessment and selection of inspection interval based on LNG complex. So here we have like the basis what we have used for the selection of the interval. Here, if you see the MOC, installation diameter, operating temperature, operating temperature in Fahrenheit, POF, thinning, POF cracking, POF external, POF brittle, POF HA, POF mechanical fatigue, then POF overall, then consequence wise, then on-stream inspection, on-stream, off-stream, or intrusive, non-intrusive, dominant damage mechanism, inspection effectiveness, then inspection effectiveness for SS, and then API 570 class, then inspection interval, and this way inspection techniques are further selected. So here, like we try to answer 5 W's: why to inspect, what to inspect, where to inspect, how to inspect, and when to inspect for the all dead legs. Mean the applicable damage mechanism are identified, what to inspect dead leg and nipples register prepared, location of inspection and the suspected location of defect also identified on the isometric drawings, then applicable entity techniques, inspection data, and inspection interval. Then developing the inspection plan. The key element of data for the development of an inspection plan is the likelihood factor. The key considerations are high total likelihood factors, high overall risk, the likelihood factor per damage type, then short or zero probabilistic remaining life. So is a Muslim country prayer for the call for prayer is ongoing behind my scenes. So since our participants are from all religions, so just informing you the sound coming is the call for prayer from the All Muslim Mosque in Abu Dhabi. So here task list, like what kind of inspection we have to carry out is a visual inspection, UT gauging, UTS, UT chime, RT, MPI, or vibration measurement. So all those types which are applicable are identified for each particular tag of the dead leg. Logistic requirement, like what kind of preparation we need for mechanical preparedness, HST caution, access and scaffolding requirement. So these all requirements are also identified for each piping tag, and this is the hierarchy of the data. Then inspection plan, which is drawing wise, it's marked, and you can see the drawing here, which is attached, and where whatever inspection techniques are required to be applied, that is marked on that particular drawing. Inspection sketches. So this is like inspection sketch where we need to go for the inspection, like technique wise, what we need to cover here. For example, 100% visual inspection, UT gauging as interval of 1.5 meter with 100 mm grid thickness average. Then for 2 inch, greater than 2 inch diameter, UT scanning at 25% of piping bends. Then MPI for 10% anchors, PRT for 20% of the small bore connections, vibration measurement applicable for the small bore piping greater than 6 inch length. Then UT chime 10% piping resting on supports. These techniques are identified to cover complete piping system, including the dead legs. Then these are like a sample inspection sketch for like a bridle of a tank. So here all the level gauges and PSVs or vessel, various components are shown where inspection is required to be done. The techniques are given to carry out the inspection as applicable, including like external visual inspection, UT gauging, PRT, and other techniques. So this is basically inspection summary, the inspection guideline or passport report of that particular dead leg and piping system. So this is how it is generated. Then interval between piping inspection shall be established and maintained using the following criteria. Just informing you how it is done: corrosion rate and remnant life calculations, piping service classifications, applicable jurisdictional requirement or the regulatory requirements, then judgment of inspector, piping engineer, corrosion specialist based on operating conditions, previous inspection results, and current inspection results and inspection results and conditions of the actual condition of the piping system. So if you see here, the general like interval class 1, class 2, class 3, and class 4 as per API 570, these are the interval 5-year, 10-year, and 10 years for all the classes. But in this particular client, they went with 3 years interval rather than 5-year interval. Then the selection of the inspection technique, location, and inspection interval is prepared based on service, MOC, and type of equipment. For example, the main locations for NDT application for piping system are selected around and at the bends, as accessibility of erosion and corrosion are relatively high at these locations. Location of NDT application is also selected for straight portion of the pipe on various points to assess the condition of pipe, which might be affected by thinning, pitting, and other cracking damage mechanisms. Then following inspection techniques are preferred: visual inspection, profile radiography, UT gauging through microprobe for the small bore, UT scanning, dye penetrating testing or DPT, vibration monitoring and measurement for small bore. Here, priority wise dead legs, like we have based on the risk or the applicable conditions, the priority 1, like in one area of the facility, like a 255, priority 2, 525, and priority 3, 142, and priority 5 priorities, these dead legs were identified for inspection. Similarly, for other areas of the plant where total number of dead legs were 4828, so the priority was defined accordingly. Now, inspection interval based on RBI criticality and piping class wise, we have followed that high, like class 1 and class 2, 3 years, not 5 years, then 6 years for the class 2, and 9 years for the other classes. So we remained within 10 years and 5 years interval as defined by API 570 class 1, class 2, class 3, and class 4 requirements. Then, like what kind of like where we are using RT small bore type, the preferred orientation of SBC to be inspected at 6 o'clock to predict and decide the inspection interval based on these inspection results. That was the aspect what we have used. So here, list of dead legs for each unit. If we see that unit 11, unit 12, unit 13 is the same aspect which I showed earlier, is a more visible condition. This slide has also been presented earlier. These other area, dead legs, how the unit wise we can show the various kind of dead leg. Total are 28 types. Then count of dead legs for visual inspection, basically like where visual inspection was carried out, the medium side, low, and very low. So, but, however, like recommended piping to be inspected 100%. Then recommended piping again, medium also 100%. For the low, we have given 75%, or very low 50%. At least inspection, visual inspection should be carried out with this ratio. Profile radiography wise, this is a percentage given, like a 25% for the high, and 20% for the medium, 15% for low, and 10% for very low. All are included in the profile radiography program for the small bore. This is 2014 results. Then there are certain vibration monitoring in 2014, 17, and 20. This is the plan which they were following at that time, because the study was done almost 12 years ago from today. So concerned recommendations, the baseline survey should be conducted for all small bore piping systems or nipples. This baseline result should be used for future quantitative RBI analysis. This report should be used to plan inspection along with VAIL-Plant software specifically prepared for the LNG complex. The target corrosion rates should not be greater than design corrosion rates. In case these corrosion rates are increasing, proper corrective action to be taken. Operating in valves to be maintained as specified in the process design basis. Monitoring of dead legs and small bore connections to be done. Listing and monitoring of pipe directly resting on steel support to be done. Then, based on Velosi experience and failure accident history, review of different oil and gas and petrochemical plant, more focus is recommended for critical dead leg, small bore piping system and nipples. Corrosion under insulation can be best prevented by using appropriate paint, coating and maintaining the insulation or sealing vapor barriers to prevent moisture ingress. High quality coating properly applied and can provide long-term protection. Moreover, low chloride insulation should be used on 300 series assets to minimize the potential for pitting and chloride SCC. It is not usually possible to modify operating conditions. However, consideration should be given to removing the insulation on equipment where heat conservation is not very important. The vibration-induced fatigue can be eliminated or reduced through design and the use of supports and vibration dampening equipment. Material upgrades are not usually a solution. Install gussets or stiffeners on small bore connections. Eliminate unnecessary connections and inspect field installation. Vibration effect may be shifted when a vibration section is anchored. Special studies may be necessary before anchor or dampeners are provided unless the vibration is eliminated by removing the source. Microbiologically induced corrosion MIC can be prevented by proper application of biocides, which will control but not eliminate microbes so that continued treatment is necessary. Wrapping and cathodic protection underground structures have been effective in preventing MIC. Corrosion inhibitors may be required to control amine corrosion within acceptable levels. Liquid metal embrittlement can only be prevented by protecting metal substrate from coming into contact with low melting metal. Once cracking from LME has initiated, grinding out the affected area is not an acceptable fix. Scale and debris accumulation should be removed and cleaned regularly to prevent under-deposit corrosion by flushing. A moderate to a severely scaled system will begin experiencing corrosion as soon as a surface has been covered. So the applicable practices, what we use for this case is also same: APA 570, 571, 574, APA RP 580, APA RP 581, ASME B 31.3, process piping, and UK Energy Institute guideline for design, installation, and management of small bore tubing assemblies. So this concludes our presentation. Now we'll take the last part of the questions, where you have you will be given floor to ask the question by telling your name, your company, and location, so as you can also be recognized by other participants. So a big number of people are participating this event, this webinar. So we may not be able to attend all the questions, but we try to attend maximum number of questions as we can. Right.
Okay, sir. The question is from Ali Riza Ashuri. We have allowed you to speak. Could you please ask your question? Ali Riza Ashuri.
Hello, sir. Good afternoon to you. I'm joining to the webinar from the Norway. Just I'm wondering to having the question about this. Shall we consider the exhaust piping for the dead legs? Because this the corrosive exhaust material is passing through the pipes. And this pipes is going to join into exhaust, and sometimes the drain pipes, and there is some dead legs, and there is a risk of the corrosion. Shall we consider and categorize this section of the pipes as the dead legs?
See, exhaust pipe generally, is
Yeah.
always active, right? Always
Yeah.
active. So if it's always active, it cannot be defined as a dead leg. However, if any drainage system which is operating on and off, that would be called as a dead leg, or any exhaust system which may be operating once upon a time situation, then it would be called as a dead leg by definition.
Yeah, okay, sir. Okay,
So
thank you.
like a general definition, PSVs, outlet lines, or a blow down valves generally are called dead leg because they are not in operation as a general, but they are operative whenever it's required to be operating. So that is the definition of a dead leg and normal operating piping system.
Okay, sir. Okay, thank you.
Sir, next question is from Mr. Guru Murthy Silvam. We have allowed you to speak. Could you please ask your question, Mr. Guru Murthy?
Hi, good afternoon. Can you hear me, sir?
Yes, sir. Welcome.
Hi, my name is Guru, working in the Qatar offshore for Velosi, Ocean field. I have two questions. First one is for regarding the damage, type of damage we expected in the dead leg. There was a slide that shows that there was expected damage mechanism is a general corrosion. Could you explain to me under what condition or what situation we can expect general corrosion in the dead legs? So far, I was working as a
Okay. First, we answer this first question, then you will be given a chance to ask your second question. See, in normal, like a dead leg is a part of the main process system. Okay. So as a first scenario, we assume that whatever the damage mechanism which are applicable on the rest of the operating piping system, same is applicable on this dead leg as well. Okay, sir. So first is, as per your normal corrosive conditions are fluid and the matter of material of construction, whatever the correlation comes and what damage mechanism we select based on service and material combination, same are selected. Then on top of that, there's one additional damage mechanism which is added on by the dead leg is the no flow situation. Due to no flow situation, there could be some like you say some stagnant fluid, there could be some SRB growth, there could be some like sludge which is also in the bottom, and under that sludge deposit. So that is a stagnant fluid corrosion or the bacterial corrosion, which may be localized or generalized. It cannot be generalized, it could be localized also at that particular location. So that is one additional damage mechanism what we take along with, let's say, since you are from the upstream side, we have a CO2 and H2S combined corrosion mostly, right? And in addition to that, we will be taking this additional corrosion due to under deposit corrosion. Okay, sir.
So that's the reason for asking me. Basically, there is no constant significant flow, there will be a chance for general corrosion. But most of the cases will be for the localized corrosions on the dead legs.
I always prefer to say localized corrosion rather than generalized corrosion. It is a mostly localized corrosion, maybe 6 o'clock position due to dead leg, right? So that is a localized corrosion. If you perceived as general, maybe some wrong message from my side, but the dead leg is causing mostly the localized corrosion, and it would be at a 6 o'clock position of the piping system.
Yes, I was a little bit confused because I was started my career from my NDT technician, RAD technician, and currently working as OIS.
Yes.
So I haven't seen any like general corrosion as go along the piping. So most of the cases, 99.9% is localized loss.
Yes. So
thank you.
Go to your second question, sir.
For explanations.
Guru,
I seen the slide. Yes, sir. The second one is regarding the flushing guidelines you showed in the webinar. Is based on the which standard, sir? I didn't get
API
any standard cross-referring to.
See, both standards are referring like if you take the piping side on the, especially the bridles on the vessels, right, and or the bypasses of the pumps, right, and if we don't do that part, it can have a high corrosion. So this is as per the API 570, 574 guidelines.
All right, sir. Thank you, sir. Thank you for information.
Next question, please.
So next question is from Mr. Raisur Rahman. We have allowed you to speak. Could you please ask your question, Mr. Raisur Rahman?
Hello, can you hear me?
Yes, sir.
Okay. My name is Mr. Raisur Rahman. I am from Olympia Chemicals Limited, Pakistan.
Welcome,
I am
sir.
working in project department. Okay. Sir, I want to ask what is the criticality of dead legs? Because I am in project department from last 4 years. I have never heard of this term dead legs. They never discuss in technical documents or design. If they are not discussing it in technical documents, why are these dead legs are so critical?
See, it varies like in which kind of industry you are working, right?
Yeah,
If you come to oil and gas sector, right?
yes, yes,
And if you open API 570 and API 574, even API 580, 581 standard, and you write the word dead leg or dead dash leg, you will find
yes,
many topics on those standards, right? And if you go to normal operating guidelines for the
yes,
any operating facility, so you have two pumps, for example, pump A and B. One of them
yes,
is operating, other one is not operating. So there is a
yes,
guideline like you have to give equal chance to both pumps, otherwise the second pump area will act like a mothballed or it will act like a dead leg, and there would be very high chance of corrosion in that particular portion of the piping system attached with non-operating pump. Similarly,
okay,
with your all pressure vessels, whether separator, whether it's a reactor, whether it is like a knockout drum or a filter, there are certain
yes,
instruments attached to give signal to
yes, yes,
control room. And those are through the nozzles, and those nozzles mostly no flow or a flow is
yes,
stagnant. So as per the industrial practice, the minimization of the dead legs, minimization of use of the small bore connections is always encouraged, right?
okay,
And that has to be taken care as a part of the best design. Okay, sir.
okay. So it's only critical.
If your company is not there, you can
Yes,
go back and show that incident which occurred in a chemical plant in Houston, which caused
okay,
a major disaster. And there are many incidents, if you go to Google, many incidents of failures are due to the dead leg failures occurred in the industry.
okay. Thank you, sir.
Welcome.
Sir, next question is from Mr. Nasid Ismail. We have allowed you to speak. Could you please ask a question, Mr. Nasid Ismail? Okay, I guess Nasid
Okay,
is not
Mr.
available.
Nasir's question is not relevant to today's topic. He's saying, hello there, in terms of sustainability, what are the initiatives taken in the current scenario to improve energy efficiency? No, we are focusing on the integrity management of the facilities to avoid failures at the facility, leakages, and as a subsequent effect of those leakages or ruptures, which can turn into fire, and that fire can burn the plant or can kill the people. So our focus is not on basically energy efficiency. Our focus is on the energy integrity, infrastructure integrity, and the avoidance of the failures at the facility. How we can do that. So we are not covering this topic today. Okay, next question.
Hi.
Next question is from Mr.
Yeah.
Hi.
Sorry, Nasidio. Actually,
Yes,
I
Nasir.
have another question as well. Yes. Like why I mentioned sustainability is because some companies like GE and Coca-Cola companies are using sensors to identify dead leg in their plants. So, but you have mentioned there are no specific sensors being used to identify the dead leg when someone asked you this question way before. So there were
No,
some
you see,
situations.
maybe there's a misleading answer, or maybe you could not hear me properly. I didn't like comment on like a sensor cannot be used. Sensor certainly can be used to see if there's any piping system is having flow inside or not. Sensor can be used certainly. Here, what oil and gas industry from where I'm coming from, API 570, API 74 even have given clear guidelines Even the standards made by Saudi Aramco or Shell or ADNOC, they are giving clear guidelines that these kind of like a geometry of the piping system is considered dead leg. This kind of scenario in the flow pattern is considered dead leg. This is not considered dead leg. So if it's a dead leg, probability of failure is taken one level more than the normal piping system, and there should be a specific inspection program to manage the integrity or to basically assess the health of that piping system, which is considered as a dead leg, because there could be high level of corrosion at 6 o'clock position in those piping system based on their condition or vertical or horizontal orientation. Okay, sir. So we are
Okay,
not
thank
saying
you.
sensor cannot be used. Sensor can be used to see whether flow is there, flow is not there. But as a process engineer, as a normal plant configuration, we know where flow is there, where flow is not there. It could be low flow, it could be high flow, but when we say dead leg means no flow. Okay, sir.
Okay, thank you. Yeah, thank you.
Okay, sir. Next question is from Mr. Gutina Shri Naga. Could you please ask your question?
Yeah, good afternoon, sir. Can you hear me?
Yes, yes.
So we have an offshore platform where there are multiple decks like middle deck, mezzanine, and cellar deck and the main deck. So we have a gas pipeline which is running from the subsea line, from deep water pipelines to shallow to deep water pipeline. So in that pipeline, we have a provision at the end of the pipeline. We have a branch which is going onto the main deck, and in the middle deck the gas will flow. The main deck pipeline, which at the end we have a before the end we have a isolation wall, and at the end is we are using it for pigging. So can we will we consider that as a dead leg, and how can we show that that line has some liquid inside it after pigging is done?
See, there are two parts when pipeline. See, normally there is a one pig receiver and one pig launcher. Pig launcher could be either side, and there should be other side is the pig receiver. Like mostly, pig launcher would be at the platform and at the production side, and receiver would be at the receiving end. Generally, one is intelligent pigging, which is done to ascertain the condition of the pipeline by MFL or UT technique. Other one is normal pigging is done for cleaning of the pipeline. See, this cleaning of the pipeline sometimes is done once in a 15 days, once in a week, once in a month, depending upon the flow conditions. And that is done for the cleaning of the pipeline and pushing the like a more condensate which might be accumulating at the bottom to the production site where the results are there to the CPF. So the purpose is to minimize the corrosion and to increase the flow rate, or to also minimize the chances of slug which can come in a bulk stage and can overfill the slug catcher or the separators. To control that, this kind of pigging is done. So that is a normal phenomena, and this pigging is generally more useful for the cleaning and the life extension of the subsea or onshore pipeline. But when it comes to the component of the pigging system, so there are a lot of piping at the pig itself, and bypass of the pigging and bypass of the line. So those parts are considered as dead legs or the mothballed portion of the plant, because that is used only once in a month or once in a 6 months or once in a year. So that part has to be taken care properly, which are the bypassing system of the production of the normal pipeline route. So this has to be considered that way. Okay, sir.
Uh, yes, sir, yes, sir. But here what I see is we have an MOV also before the uh, pig launching point. So
Yeah.
whether this line till the isolation wall to be considered as dead leg, and after the
Yes,
isolation
portion wise, wherever there's a no flow situation in the normal life, okay, as a process engineer, as an inspection engineer, we know that, and that has to be considered as a dead leg. And this portion, like in the pig launcher and receiver bypass lines, should be considered as a mouthball, because you need to, after running the pig, whether it's a cleaning pig or inspection pig, so you have to flush out those lines, you have to clean them, and you have to also purge them with nitrogen. So there should not be any corrosion when there would be no operation going through that system. So that's we call it mothballing process of the pigging system. So that these dead legs has to be considered as a mothballed portion of the plant and has to be dealt accordingly. Once mothballing done, cleaning, purging done, there should be no corrosion internally, and it is normally managed this way. Okay, sir.
Yes, sir. We did the nitrogen plugging and all, but till then, after that also it should be considered as jet lag or not. That is what we are facing
No, see,
because we are
all
raising the
parts where
practice
there is
list.
no regular flow, where the part of the plant wherever if it is a no regular flow, it will be called as a dead leg, and dead legs are three types: one permanent one, number two operational one, number three mothballed one. So this would be coming either operational or mothballed portion. Okay, sir.
Okay, okay. Thank you, sir. Thank you.
Thank you. Okay, sir. Thank you very much for the day. We tried to answer most of the questions. It was one of the highest attended webinars from our side. So if there are more questions, you can send also through our email address, and we'll try to answer you. You can also call us. It is our pleasure to assist industry engineers with the best of our abilities, and we look forward to meet you during next webinar, which would be 1 month from now, another topic. Till then, thank you very much and bye-bye.